Hey everybody, welcome. Good to see you, some of you. Great. Hope you guys had a nice weekend and welcome to Abstract Math. So the plan today is just to go through the next worksheet. So we'll be working with worksheet number 2. So if you've got that out, that would probably be useful as we go through the material today. But before I get started, any questions from anybody? So good work on the quiz, kind of had a chance to look through your work there. So we'll kind of start with that, make sure there aren't any questions remaining with that, and then we'll continue on. So just a couple of things before we get going. I just want to point out that all of the videos are up on a YouTube channel on a playlist for the semester. So you can go, and that link is in Canvas. I just want you to know that usually I just post, sorry, you don't need to listen to me twice. I just post like one video, even if it's long. So this was like the 60 minutes that we had from last class, and I just tag them over here. So you can see kind of the time tag. So I get that you don't want to go through a 50-minute video if you just have a question about question number 3. So you can just click on that link and it'll take you to that part in the slides. So I get that you probably don't want really large videos up there, but I think it's just easier for me to time tag it rather than post like 10 5-minute videos. So it'll all be there. But if you do have any trouble finding anything in there, just let me know. And usually these are up. So today's is being recorded, and I'll try to get this up at some point tomorrow afternoon. So just keep an eye on that. And while I've got my browser shared here, I do just want to point out that for this week, all of the materials are up. Don't forget, you've got a homework assignment that's due on Thursday, and that's going to be on the material that we discussed today. So if you looked at that homework assignment and you had a lot of questions on it, that's probably normal because that's what we'll discuss today. But the quiz for Wednesday is up, and you've got a video and slides to go along with that. So that's kind of be the flow for each week is quiz before class. Homework for now is going to be due on Thursdays at some point. We're going to switch that to Mondays, but I'll let you know about that. Any questions? Okay, so yeah, so I want to kind of start with the material that you guys looked at for the quiz, and which were what are statements, how do we combine statements, how do we negate statements. So just recall that a statement, right, is something that has to be either true or false, right? So there's no ambiguity with it. So for example, this first one over here, 121 is a prime number. Is that a statement? So let me just quickly launch a poll. So do you think, sorry, wrong poll. This is the poll I want. Do you think this is a statement? And if so, why or why not? Okay, take another 10 seconds, please. I'll take chats or polling, that's great. Okay, so just to kind of share the results that came in, pretty much everybody thought it was a statement. This is a statement because it is either true or false. And in fact, 121, right, is equal to 11 times 11. And so since it can be broken down into a product other than just 121 times itself, this is false. So yes, it is a statement, but it's false. That would be a yes for is this a statement? Let's see. So for the next one, just going to relaunch this, go wash my car. Do you think that is a statement or not? Okay, awesome. So just to share the results that came in quickly, right? So this is not a statement because this is a command, right? This is not a true or a false statement. If I said, she washed my car or something like that, then that would be a true or a false statement. But this is a command. It's not true or false, so this would be a no. Something like this is actually a sentence, right? We just write it more concisely with the notation. And so something like this, we would say it's true for some values of X, but it's not true for other values of X. So since this statement is sometimes true and sometimes false, we would say that this is not a statement. We would call this an open sentence. And what we mean by an open sentence is it depends. Right? So X equals 0 would make that a false statement. X equals something like -1, I think might make that a true statement, or I don't know, I'm trying to solve this in my head. I think actually, yeah, 6 and -1 would be the solutions here, something like that. So for some values of X, this would work. For other values, it would not. X equals 6, X equals -1, it would work. Okay, so any other questions about kind of how we determine whether something is a statement or not? Okay, so yeah, just a couple of things. I think I talked about this, but just keep in mind, the first homework is due Thursday at midnight. And so I just want to talk about a couple of things before we go and do some work together, and that we're going to use some breakout rooms throughout this semester. And so I just want to make sure that it's clear what's expected when you go into those breakout rooms. And so it's really nice that we're all distanced here if it's possible to be able to see your classmates. Definitely have your microphones turned on, and it's great as we get going and we're writing proofs if you can also use the screen share in your breakout rooms. That helps when Lindsay or myself go into the breakout room to see the work that you've been doing up to that point. And, in addition to that, just, treat others with respect. We're not here to all agree with each other. So there's going to be times when you are critical of something that somebody is saying. Please don't take offense to that. If someone is asking you, I'm not quite understanding you, and just be mindful, like there could be ways that you phrase things that might be rude, like you're talking gibberish, or like, hey, I'm not quite following you, what's going on. Once you get to know each other and you feel more comfortable, feel free. But I would say, as we're getting to know each other, let's just try and be a little bit respectful. Yeah, give everybody a chance to contribute. I think it is an important point here. So try not to have one person dominate the discussion when you're talking about these things. And yeah, be positive. Like, hey, that's a great idea. I didn't think of that. That's always nice to hear from your classmates as well. And if someone's being a little bit shy or something like that, don't need to put them on the spot, but they just might be asking for an invitation. So it won't hurt to just say, hey, we haven't heard from you. Do you have anything you want to share? Yeah, and I'll just say the point of this exercise of going into breakout rooms is because you learn a lot more when you make mistakes. And so if I just go through class and don't make any mistakes, it's going to be a really passive process for you. And when you try and do your homework on your own, you realize you're going to run into some roadblocks. And so it's good to run into those roadblocks together and kind of work through them. Okay, so I am just going to open up the worksheet, that worksheet 2. So it looks like this. So we've been going through some of these. When I put up the solutions, I'll just write up whether these are statements or not, and you can check your work at home. But I think I want to move on to some of the more challenging stuff in this chapter. So there are different ways that we can combine two statements. So again, statement P and Q usually refer to like a sentence with a letter P or a Q. And so one way that we can combine two statements is with a conjunction, which is this wedge looking thing. And this is a conjunction with an and. So if you have seen set theory, we certainly will. It's kind of reminiscent of the intersection symbol. We just make it pointy. So this means both P and Q need to be true in order for that conjunction to be true. Whereas when we have this symbol over here, this is an or statement. So this is going to be true if at least one of the statements is true. So if either P is Q is true, Q is true, or both P and Q are true. And then we've got the negation of a statement, which we indicate with this little tilde before the P. So that means the opposite of statement P. And the negation of P is just the statement which is false when P is true and true when P is false. So it's the opposite of P. So if we're taking a look at question number 2, right? Colorado has mountains. That is true. Colorado borders an ocean, right? That is false. And so if we are thinking about the statement P and Q, Colorado has mountains and Colorado borders an ocean, would that be true or false?
False.
Right. That's false because this one is false. So that's what makes that one false. Whereas if you have an or statement, then we just need one of them to be true. So that would be a true statement here because P is true. And we just need one of them to be true. And in this case, if we wanted to think about the negation of Q, this would be one way that we could state that would be Colorado does not border an ocean. That's maybe not the most elegant way to negate that statement. So oftentimes it's nice to write a negation without just putting not in the sentence. And so maybe a slightly more elegant way, I don't know, would be something like Colorado is landlocked. I don't know if that's any more elegant or not. But there are different ways. It's not a unique way that we can negate a statement. And so is that a true or a false statement? What do you guys think? You can, for those that have a camera on, that's a quick way to do it. Okay, thank you, Nicole. Thank you. Yeah, that's right. So because Q is false, this one would be true. So that's a really quick recap of the videos, right? And one nice way, as we'll see today, to kind of organize these truth and falseness of combined statements is using what's called a truth table. Okay, so any other questions about that material before we move on into some new stuff that you guys didn't read about, conditional, biconditional statements? Okay, so I would say most of the semester, I don't want to put a percentage on that, is going to be dealt with proving or disproving conditional statements. So these are things that we see all the time in mathematics. If f is a continuous function, then here are some properties that it needs to satisfy. So we're going to mainly be focusing this semester on establishing, proving something is true or false of the form if P, then Q. So a conditional statement is exactly that. So we have two statements, but rather than saying P and Q or P or Q, what we're saying is if P, then Q. And so when we stated it, the ordering here does matter. I should mention over here, when we're looking at these conjunctions and disjunctions, right, the truthfulness or falseness of these statements, the ordering doesn't matter whether we see P and Q, Q and P, or whatever. When we're dealing with a conditional statement, certainly the order now does matter. It does matter what we're assuming, and then it does matter what we're trying to prove follows from that. So let's consider the following statement. P is you ate all of your vegetables. That's either a true or a false statement, right? Either you did or you didn't. There's no ambiguity there, as well as you will have dessert. And again, this is a true or a false statement. Either you do or you don't. So very typical conversation you might have would be, if you eat all of your vegetables, right, you will have dessert. So this is if P, then Q. And so one way that we would like to determine whether the conditional statement is true or false, the conditional statement being true or false, again, is going to depend on whether individually P and Q are true or false. So one way that you can think about this would be, if P is true and Q is true, is this statement a lie, right down here? So in other words, what this is saying is if you eat your vegetables, and you get dessert, then this original statement, if you eat your veggies, you will have dessert, is this a truthful statement or a lie? Does this contradict what happened up here? What do you guys think? Okay, so Kenneth says that's a good one. Yeah, and so if you eat your veggies and you get dessert, then right, your parents haven't fibbed to you. They, in fact, are telling you the truth. So if both the hypothesis and the conclusion are true, then altogether the conditional statement is true. And let's think about B. Okay, now we're going to think about this part over here, this row in the truth table. If P is true and Q is false, would your parents have lied to you? So in other words, you eat your vegetables. So P is true. Q is false, so that means you do not get dessert. Then comparing this truthfulness of P and Q to the original conditional statement, is the original conditional statement now a lie or is it still true? All right, Like, yeah, so I see a thumbs down, right? That would be a lie. You would be pissed if you ate your vegetables and then suddenly you're like, nope, sorry, deal has changed. You're not going to get dessert. So this is one way to try and think about whether or not truthful conditional statements are true or not. So I'm going to give you guys a second since people are a little bit hesitant here to chime in, and I'd like to hear what everybody is thinking, to think about the last two rows in this table. So in other words, for D, we would want to think about you did not eat your vegetables. Okay, but you did have dessert, right? So this would be P is equal to false, but Q is equal to true. And so now what you'd want to say is, okay, if this is the reality of the situation, does that contradict the original conditional statement? So I'd like in your groups to just spend not a whole lot of time, but just discussion in parts D and E, whether, oh, sorry, I skipped one. We're going to think about C, N, and D to complete this table. Does that make sense? Okay, so for those of you that may or may not have breakout rooms, it's just kind of good to see how these go. So at this point, you should see that a room has been opened. When you click on that room, you're going to be sent there along with the other people in your room. And Lindsay and I, just so you're prepared, we might barge into your room every so often. Okay, thanks. And Lindsay, if you have a second just to hang back in the main room. Yeah. Okay. Well, great. It's nice having those little rooms, give a chance to get to talk to each other on a more smaller basis. Okay, so far we talked about the first two rows, and now part C is asking us to think about this one, and part D is asking us to think about that one. And just talking with the groups that I spoke with, there was some discussion about, well, the statement says if you eat vegetables, you do get a dessert. So it was very clear that B was a lie, because here's a student that did eat their vegetables, but then the parents reneged on their agreement. The question is here, it's a little bit more of a gray area. So we'll see if there are any aspiring lawyers out there to see whether someone has perjured themselves or not. But children are very good about this logic. And so if a child does not eat their vegetables, but they still get dessert, right? That doesn't contradict what's over here, right? This statement only tells us what happens if you do eat your vegetables. There's no implication in this statement about what's going to be the effect if you don't eat your vegetables. So if you don't eat your vegetables, but you still get dessert, it doesn't mean that this was a lie. So this would be a true statement, logically speaking. And in part D, this would be something like you don't eat vegetables, and you don't get dessert. Right, again, this isn't contradicting anything that was said in the original statement. So this is not a lie either. So this tells us the only way a conditional statement is going to be false is if the hypothesis is true, but the conclusion is not true. If the hypothesis is false, like in the last two rows, then the conditional statement is going to be true no matter what the conclusion is. Okay, any questions about those? So there's some subtle subtleness going on with these agreements, with this if-then condition. Okay. And so the last type of statement, last type of combination of statements that I want to talk about are these biconditional statements. So this would be if P then Q and if Q then P. A biconditional statement again is kind of would be taken into account. Does P imply Q, and at the same time does Q imply P? So if P is the statement a triangle is isosceles, and Q is the statement a triangle is equilateral, right? Well then, right, if P implies Q, it doesn't necessarily guarantee that when we switch those around, it's going to be true. So if a triangle is isosceles, does it have to be equilateral? Right, so that's no. So this is false. Here's an example of an isosceles triangle, but it's not equilateral. Whereas if we flip this around, right, suddenly that would now be a true statement, since every equilateral triangle has to also be isosceles. So point being here that the ordering of these conditional statements matters. Where it's not important for a conjunction or disjunction. And it's likely that you've seen language like this in math classes, if and only if. And so this is what we mean by a biconditional statement. So when you see something like P if and only if Q, then that means P if P then Q and if Q and P. So it's and statement, and it's connecting two conditional statements, right? So now we're starting to embed things in each other. So now this becomes an and statement where the hypothesis and the conclusion, or excuse me, where the two statements that we're connecting with an and are each conditional statements. So before we dealt with P and Q, now we're dealing with if P, then Q, and if Q, then P. So I would say, biconditionals, these are kind of the top of the food chain in terms of complexity of statements. So an example of a biconditional statement would be something like a triangle is equilateral if and only if it's equally angular. And that is a true statement. So if it's equiangular, it has to have all the same sides. If it has all the same sides, it has to be equiangular. So this would be an example of a biconditional statement. And I'll just say that in mathematics, I don't know, I was scarred at a young age. Like my second math class I took in college, I had a professor in linear algebra who would just cold call on all of us and ask us to define things. And if we gave a definition that didn't have if and only if in it, he would berate us and say like, Jesus, how could you get this wrong? And so by the end of the semester, we had about 10 people left in the class. It was the 10 people who were okay with getting yelled at, I think. But point being, yeah, you just want to be a little bit careful that when we say that P if and only if Q, it's really saying that P is equivalent to Q. And that's oftentimes how we define things in mathematics classes with an if and only if statement. So we could say a triangle is equilateral if and only if all of its sides are equal to each other, something like that. And so now the question is, how can we figure out a truth table for a biconditional statement? And let me say the notation that we use for that is this double arrow over here. So this would be, we would want to determine the truthfulness of this and this. So maybe let's break this down separately. So over here, I'm going to have P, Q, and P implies Q. And let's just kind of recap what would be true about P than Q. So remember, like if both of these statements are true, then this is going to be true. If the hypothesis is true, but the conclusion is false, this was the only situation where the parent was lying, right? Where that contradicted the original statement. And then we said, okay, well, in the case when the hypothesis is not true, then there's going to be no way that we come up with a contradiction. So this was the truth table that we just had for the conditional statement before. And now let's think about using these same first two columns of the truthfulness of P and Q. What would that say about when we switch the order of the conditional? So in this case, if Q is true and P is true, then what goes over here? Yeah, that would be a true, right? Thumbs up there. So if both of the hypothesis is true and the conclusion is true, then that's going to be a true statement. Over here, now what we're saying is if Q is false, right, but P, so we're getting Q's truthfulness over here, Q is false, P is true. If the hypothesis is false, but the conclusion is true, then what would be the truthfulness of this statement? Yeah, okay. So remember, if the hypothesis is false, if Q is false, then no matter what the conclusion is, overall this statement's going to be true. And so notice that, right, the ordering does matter. We got a different result depending on which way we order this. And over here, again, if we say that Q is true, and now we're going to say P is false, what happens if the hypothesis is true, but the conclusion is false? Yeah, that's a thumbs down. Thank you. And again, that's different than what we got the ordering the other way. And when both of the statements are false, then we're not going to get any contradiction there. So that's okay. Any questions about how we came up with the two truth columns for the conditional statements? And so now we want to come back and fill in this biconditional table. So remember that the only way an and statement like this one is going to be true is if both this and this are true, right? We need both of them to be true. So if I have a true and a true, I see that this one is true and that one is true. So that's great. If we've got true for P, but a false for Q, you can see that both of these statements are not true, right? So therefore, the conjunction of them is not going to be true. In other words, that's going to be false. And for the same reason, we don't have two trues over here. We have a true and we have a false, that this one is going to be false. And this last one, we have a true and a true. So this one is true. So kind of one way to maybe summarize the truth table for a biconditional statement is it's going to be true if P and Q are both true or P and Q are both false, right? Otherwise, if P and Q, one of them is true, one of them is false, it's going to be false. So that's what I mean by this. Okay, if they have different truths, meaning one of them is true and one of them is false. And let me just say that, you know, this logic side of things is going to be really important when we think about different ways that we might be able to prove that a statement is true or false. Sometimes we might try proving that the negation is false, and that might imply that the original statement is true. So these logic tables are going to come back and help us with different proof techniques. Any questions? Okay, so so far we've talked about ways that we can combine statements, conjunction, disjunction, conditional, biconditional, and we've talked about how to negate a single statement. And so the last thing I want to talk about is how can we negate a combination of statements. And so one thing to keep in mind, just to do a little bit of scratch work, and that is if we're dealing with a statement and its negation, right? The negation of P means when P is true, the negation would be false, and when P is false, the negation would be true. So if we come over here, and I just want to say, let's focus on kind of this part of the piece over here. So we have P and Q, and then we have, if we connect them with an or statement, right, then we see that the statement, when we connect it with an or, is true as long as at least one of them is true. So we have only one situation which is false. And right, if I wanted to negate the or statement, so notice the parentheses here. First, joining P and Q with an or, and then I'm going to negate that whole statement. Whatever this statement is, it should have the exact opposite truthfulness as this one over here. So if that was true, the negation should be false if P and Q are true. So when I'm trying to identify the negation of this statement, I'm trying to see, well, what statement would have the exact opposite F's and T's, right? This had T, 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 F. I would want to look at the negation of that would be, well, P and Q are both true. It should be false. And over here, we can see that equivalent to this would be, it's the same thing as saying we could negate P and Q and join them with an and. So the negation of a disjunction is we negate both and change the or to an and. And when we do the negation of a conjunction, we do the same thing. We negate both P and Q, and we're just going to flip the way that we join them. So when we join a conjunction, we join it with an and when we negate a conjunction, we wind up with an or statement. So this is a busy slide for a truth table. The short story is here is a way that we can negate these combined statements. And if you're curious, like, where is the proof for that? Again, that you could verify by coming down and working through the details of the truth table. Any questions?
So basically the negation outside of the parentheses just distributes into the parentheses for the P and the Q.
That's right. So we're gonna negate, we're gonna move that inside, right, here and here, and then we also flip this sign around when we do the negation. Yeah, and so it winds up, we negate P, we negate Q, this, or now it changes to an and. And kind of similar if we kind of compare this one, which is the connection with an and statement, we can see over here that its negation, when we change the T to an F, F gets changed to a T, and so on. It appears in the last column. So in part A, we want to negate this statement. And sometimes you can kind of just go about this from like, I get the logic of what this statement is saying and I can negate it. Sometimes it's tricky. I think it gets particularly tricky to negate a combination of statements. So something that might be useful would be, let's identify what are the statements P, what are the statements Q, and how are we combining them? All right, so P could be the 2014 Olympics. We're in Sochi. And Q is saying 2018 Winter Olympics. We're in Pyeongchang. And for those that might not be keeping up with your Winter Olympics, these are both true statements. That is where the Olympics were in each of those years. But this isn't asking us to gauge the truthfulness anyway. This happens to be a truth statement. So what we know is altogether, first of all, this statement is true. So the negation of this statement should be false. So if you're stuck on how to do this, what you could do is just write out P and Q. Then you could separately negate each of these statements. And I don't think there's a particularly elegant way to negate this other than to put not into the statement. So I'm just gonna, oops. And sorry, I'm trying to save myself from writing, but let me just rewrite this, sorry. If we were to negate these, we would have 2014 right? 2014 Olympics were not in Sochi. 2018 Winter Olympics were not in Pyeongchang. And then the negation of this would take this and change it to an or. So then altogether, the negation here would mean something like the 2014 Winter Olympics were not in Sochi, or the 2018 Winter Olympics were not in Pyeongchang. So that would be the negation of this original and statement. And notice that this statement is false because neither of those statements is true, which is good, right? So if the original statement was true, then its negation that we wrote in blue had better be false. That's a good way to check your work on that. Okay, so someone want to take a shot at negating B. So B is saying Adam is a teacher or he is a giraffe. This is a true statement since I am a teacher and I am not a giraffe, still makes this statement true. If you want to chat it in, feel free. If you want to just say it, that's great. But it's nice to hear what our classmates say. Okay, well, thank you. Got a couple people chatting in. Adam is not a teacher and he is not a giraffe. That's right. So when we are going to negate this statement, we want to make sure that first of all, we realize that or is going to change to an and then we're going to negate each of those two things. Right, so we just negate each of these things and join them together. I'll just say again, like as we're writing out things and as we're proving things, it is going to be nice to try and prove things and say things in maybe the nicest way. So this is kind of like a good first statement, like here's the procedure. I know I negate the first thing, I negate the second thing, I change the or to an and then you might just want to look at the sentence. And it might look awkward if you just kind of do it following that machinery, and you might think about, is there a way that I could explain this nicer, you know, and I don't think that's the case here. I don't think there's too much that we can clean up here. Adam is not a teacher and he is not a giraffe. Okay, are there any other questions about that? I can kind of leave C for you to practice and put up the solution to that. Yeah, okay. If there aren't, then let's think about how we can negate a conditional statement. And again, the details are down here in the truth table, but if here's the original statement, if I want to figure out what is the negation of that statement, well, it's going to be a statement which has the exact opposite truthfulness as the original. So it should have a false, a true, and a false, false. And so that comes out to be equivalent to we don't change the hypothesis, but we're going to say P is true and Q is not true, right? That was the only way that a conditional statement was false. So when we negate a conditional statement, it doesn't become another conditional statement. So just be careful about that. What we actually get is an and statement. Okay, and this is going to be really important fact when we want to prove a conditional statement by contradiction. Let me just say that, but we'll get to that in time. Okay, so in question number 7, we've got a conditional statement. If P, then Q. Then if we want to negate this statement, right, we don't change the hypothesis. Okay, so we don't change the statement P, the hypothesis, F is a differentiable function. This now becomes a and statement. And then we do negate the conclusion. So the conclusion here was that F is continuous. So the negation of that the function is not continuous. And let me just say that the original statement here, that's true. If a function is differentiable, it has to be continuous. This statement below, its negation is false. Just because a function is differentiable, I'll just say there do exist functions. Yeah, anyway, if a function is differentiable, then it has to be continuous, right? So it definitely can't be not continuous. Someone want to take a shot at the negation of 7b? Okay, I'm not prepared. Usually, if I'm not hearing from people, I'll just call on people. I don't want to call anybody out, so I just randomly generate a list of names and I go through the semester. I haven't generated that yet, so I don't want to call on anybody. But just be prepared next time. I will, and it's not calling anybody out. I just randomly generate these things. I just want to hear from different people in the class. So good. So thanks for some of the comments that were coming in. If you wash my car, you will not get an A in Math 3000. So let me say it like this. So one statement that came in is, if you wash my car today, you will not get an A in Math 3000. The next one is, if you wash my car today, and you will not get an A in Math 3000. And the last one is, if you wash my car today, you will fail. Okay, so logically, this is good. These are slightly different statements, right? So saying you don't get an A, for example, is different than saying you're going to fail. So one thing I want to be careful about, that all of these statements, and this is why it's really great to hear from people rather than just hear me do it in the right way. Does anyone see what might be wrong? These are all 3 really close and good suggestions, but does anyone see what might be wrong with all 3 of them? Yeah, That's right. They all start with if. Okay. And in fact, right, we started with an if statement. We started with a conditional statement. When we negate a conditional statement, we don't get another conditional statement back. So we shouldn't get an if then statement. We should get a and statement. So if we kind of take what Christina said, which is if you wash my car today, you will not get an A. Instead of if then, let's just connect those with an and. So in other words, you wash my car today, which is either a true or a false statement. Okay, and you did not get an A in Math 3000. So keep in mind that we take this statement and we don't need the if there anymore, right? It's not a conditional statement. It becomes an and statement. Any questions there? So I think that was something that came in on all of these responses. So I'm guessing that's something that others might have been thinking as well. So it's just worth making a note to yourself that when you negate an if-then statement, it becomes P and not Q. Okay, it becomes a and statement. Okay, I will jump over question 8 for the moment. Just to get to the last negation here that we need to do, which is how can we negate a biconditional statement? And so to negate a biconditional statement, we can use all of the information that we've talked about so far. So first of all, a biconditional statement okay, is an and statement that connects two conditional statements. And so if we want to negate a biconditional, then it's equivalent to negating this and statement. And in going from the previous line below, right, all we're saying is that when I negate an and statement, I negate each of the two things and flip the and into an or. So that's what we talked about earlier when we negated and or statements. And now, finally, we can use what we just talked about with how do we negate conditional statements. And so when we negate each of those conditional statements, right, we get and statements over here. So that kind of combines all of the previous results that we have with negations to finally get the negation of a biconditional statement. Okay. So maybe let's take a look at this last one, since we just have a couple of minutes left to try and talk about how we can negate this biconditional statement. So over here, we've got, oops. Kind of our P, a triangle is equilateral. Q is each of its interior angles is 60 degrees. So this is a true statement. But if we wanted to negate it for some reason and say, I want to prove that this is true, I'm going to negate it, and I'm going to show that the negation is false. That's one way that we might prove things. Then it helps kind of identifying what P and Q are again, if we're going to try and combine these things. So I've got my P, I've got my Q. And once I've identified the P and Q, now I know that for the biconditional, here's what the negation is going to look like. And now I can just plug in my P and not P, my Q and not Q into the right slot. You might get a really weird looking sentence, and then you might think about how can I clean up that sentence. But let's kind of see what happens. So P would be a triangle is equilateral. Then we've just got our and that comes from this piece over here. And then we're going to negate Q, which would be its angles are not 60 degrees. And so here, I negated each of its interior angles is 60 degrees by saying at least one of them is not 60 degrees, right? This doesn't mean that one of the angles couldn't be 60 degrees. It just means that all three of them can't be 60 degrees. So this is kind of the first piece. And now we can write out this second piece over here by saying, well, what is statement Q? So that's our statement Q, and then we're going to connect that with an and then we're going to put in our negation of P. So hopefully, kind of in this long sentence here, you can kind of identify where we got each of these color-coded statements in here. So just to kind of read this all, a triangle is equilateral if and only if all of its interior angles are 60 degrees. Fairly simple statement. Negating that, we get a very complicated statement like a triangle is equilateral and at least one angle is not 60 degrees, or all three angles are 60 degrees and a triangle is not equilateral. I think when you're negating a biconditional statement, you're going to get something which is a little bit clunky. So yeah, just be sure that at first you're thinking about making sure I get it right, and then think about, is there a way to kind of clear that up? Can I make that statement more clear? Okay, we're out of time. Sorry about that. So this should certainly get you going on your homework, which is due on Thursday. if you do have some questions on that, I've got office hours tomorrow from 1:30 to 2:30. Yeah, and Lindsay's got off. When are yours, Lindsay?
At 1 o'clock today,
1
and then
o'clock.
Wednesday at 9 a.m.
Yeah. So we're here. If you have any questions, otherwise, have a nice afternoon, and I'll see everybody on Wednesday.